Hello, everybody. We can start this session about the multi-FPGA hardware in the loops, about the platform for MEA power system in real-time simulation. So let's start the presentation. So today, we will have two presenters, myself, Mathieu Hainaut. I'm the offering manager of the aerospace division of OPAL-RT technology. So I'm actually managing all the relation between the customer and the market needs and the development internally at OPAL-RT and the offer that we can present. As a speaker today, we'll have also Amin Yaman. It's our power system real-time simulation expert at OPAL-RT. You have more than 12 years of experience at OPAL-RT in the various projects, especially in power systems. And now he will tell us about his few last years of implementation on the power bus in the airplane as a MEA simulation, the more electrical aircraft. So today, if we're going to go to the next slide. Today, the agenda is actually an introduction about what is the MEA power system topology, and actually what is the big challenges around that for the real-time simulation. So since the airplane is going more and more electrical, how come the simulation and the real-time can help you on that? And then after that, we'll see our solution, which is based on FPGA, so all the hardware architectures and actually our solver that we develop in this system on a chip. Then after that, we'll go for some proof of concepts, so really going step by step of the first validation of the model in software in the loops, and then adding that to the hardware in the loops application. And we have a brief overview as well and some really good data that we have on putting the concept to the part hardware in the loop, so adding an amplifier in the loops with the simulation of the more electrical aircraft. So I will let Amin start his presentation about the MEA power system topology.
Thank you, Mathieu, and welcome to everybody. So the more electrical aircraft power systems represent a real challenge for any real-time simulator. If we look at the topology we are seeing in this slide here, so it consists of a power distribution network with very short power cables and including a significant number of fast switching frequencies, frequency inverters, such as the 12 IGBT inverters that we can find at the load side. It includes also enormous slow switching frequency rectifiers, like the ATR and the TR units, and an extensive number of breaker circuits used to interconnect the different sections of the power system. So if we consider this power system from the Boeing B787 model, this power system, which is considered as one of the largest more electric aircraft power system, actually, it includes until 18 diodes rectifiers, until 4 12 IGBT inverters, and over 30 three-phase breaker circuits. So this means that the power system needs to be decoupled to maintain the simulation sample time to the desired value by assigning the different subcircuit of the power system to be simulated in different computation units. The problem here is that this power system includes only very short power cables, which complicates the power decoupling task, as we will see in the next slide. So here, from this analysis of this topology, we can figure out with two major challenges that are facing the real-time simulators to simulate the more electric aircraft power systems. The first challenge is the accuracy to simulate high frequency phenomena. So in the more electric aircraft power system include power electronic circuits that are requiring high switching frequency. So the real-time simulator needs to be able to to decrease the simulation sample time as low as possible to be able to simulate accurately or represent accurately the high frequency switching and the circuit dynamics. So if we take as example the motorized turbo compressor, which is a motor drive that we can find at the load side of the power system, those systems are requiring 20 kilohertz as a switching frequency. So for this level of switching frequencies, typically, if we can reduce the simulation sample time to 1 microsecond, this will provide a very good resolution of the simulation. So the interest here is to be able, or the real-time simulator needs to be able to reduce as much as possible the simulation sample time. The second challenge is the ability to simulate large power distribution systems. So a large power system requires a multi-processor solution in order to maintain the simulation time step to the desired value. So in hardware point of view, the real-time simulator should ensure the scalability, means that the real-time simulator offer the possibility to increase or decrease the number of computation units in order to cover large and small power systems. In terms of or in software point of view, the real-time simulator needs or should be equipped with efficient methods to ensure an accurate power decoupling between the different computation units. So here as an example, the most famous power decoupling method is the so-called stub line power decoupling interface. So this method adds a parasitic capacitor to the circuit in order to perform the decoupling. And the value of this artificial capacitor depends to the cable impedance from one side, and from the other side, the simulation sample time. So there is a relation. If the sample time is large, the computed capacitor will be large also, which will affect the original behavior of the system. So here also the interest is to have a simulator that is able to reduce as low as possible the simulation time step. So the proposed or the developed FPGA-based real-time simulator that we propose is given in this slide. It consists, or it includes an FPGA board that is leading to simulate power electronic circuits with a simulation sample time less than 1 microsecond. Using the analog and digital input-outputs equipped, integrated in the simulator, the circuit can be easily connected to a real controller under test with a latency less or around 1 microsecond, forming a real application, a real hardware in the loop application for control or any device under test. The platform integrates some Intel-based processors that are used to simulate some slow frequency phenomena, such as the mechanical parts of the machines, and also can be used to simulate controllers in what we call the software in the loop simulation, which is one of the principal steps in the real-time simulation integration process. For about the workflow to integrate a circuit from the offline to the real-time simulator and be ready to connect a real device in the loop, forming a HIL application. The simulator here can be connected or wireless connected to a PC host where the user can easily design and draw the power circuit using any schematic editor. So here we can use our own schematic OPAL-RT schematic editor. We can use the schematic editor from MATLAB, SimPower System, Plex, PSIM, etc. And then using RTLab software, the designed circuit can be compiled and the FPGA can be configured automatically. And so the circuit is loaded and ready to be, and the simulator is in this case ready to be connected to a real device under test through the digital and the analog input-output modules, or through the available communication protocols. So this is for one single FPGA-based real-time simulator, and the solution is scalable. Means that we can have such configuration. We can have a PC-based computer that is connected through the PCI connection to a series of FPGA boards that can be interconnected with the fast SFP connections like this. So for about the validation of the platform, we started really step by step. We started by the validation using the simulator standalone. Means no external device is connected. Everything is in the simulator. The power circuit is running or simulated under the FPGA, and all the controls and all the mechanical parts are running in the CPU parts. So we started first by validating the different power circuits, that power electronic circuit that we can find in the more electric aircraft power system, where we can find a family of rectifier units, such as the one shown here. We can find a family of motor drive, and we can find also a family of power converters for power supplies and battery power conversion. So all those families, for each family of these circuits, we simulated or we tested the different topology that we can find. For example, for this rectifier here, we show the 18 diode topology. We can find the 12 and we can find the 6 also. Same thing for the drives, and also same thing for the pack-2 cell multi-level. You can find the different level, POC 5, 7, etc. So all those circuits were simulated real time using our FPGA-based electrical solver called EHS. Here we give a sample of result by simulating the MTC circuits, which consists of a 12 IGBT inverter here that is driving 6-phase or 2 3-phase PMSM motors. Here we show another example of the MTC circuit with less IGBT switches. So here we show one of the dynamic tests that we have applied. Several dynamic tests were applied, and always the result is compared to the SPS offline simulation with very low sample time to ensure the most accurate results. And also we always, for all those circuits, we were getting very good result compared to the offline simulation, and the error was always, in some cases, always less than 1% of error. So once the accuracy of the solver was validated, now we need to validate the power decoupling elements in terms of accuracy and robustness toward the numerical instability. So to do so, we chose two principal feeders of the Boeing B787 power system. The idea here is to validate the stubline power interface that we see here. And since each FPGA can handle 2 electrical solvers, so we choose it to validate this decoupling elements first inside one FPGA. Means that the power decoupling element will decouple the power between two solvers running to the two feeders. Each solver is running one feeder, like as we can see in this schematic here. So here also we repeated the same series of dynamic tests as the test we are seeing here. It consists of a step on the speed reference here, and the results are a real perfect match with the SPS offline simulation. Then what we did is we started another series of tests, of fault tests. We applied several type of faults in different locations in the circuits, even very close to the power decoupling interface here. And as we can see, the result were always accurate, and the platform was always stable numerically. So no divergence, no numerical divergence was detected. So once we validated the power decoupling interface inside one FPGA between two solvers, now is the time to validate this power interface between two FPGAs. To do so, we simulate the 4 principal feeders that we find in the B787 power system. Each 2 feeders, the left 2 feeders are running in FPGA board 1, and the right 2 feeders are running in FPGA board 2, and both FPGAs are interconnected through this power decoupling element here. So we repeated the same dynamic tests and also the fault tests, and the power decoupling interface has shown a good robustness toward numerical instability, and also the losses were very small, negligible. Since the sample time used is very small too, we are talking about something less than 1 microsecond, 800 nanoseconds of real-time sample time. So once the solver accuracy was validated with the separated circuits, the power decoupling element interface was validated inside between solvers and between FPGAs. Now we were ready to integrate the full or the complete Boeing B787 power system to show the robustness of the platform. So if we need really to simulate this system completely to show that it is possible with this platform. So here we show the performance of the simulation. To simulate this complete system, we need 3 FPGA boards. As can be seen here, the board number 1 is used to simulate the body of the power system, including the generation and the ATRU, or the diode rectifiers here and here. The second FPGA board was used to simulate all the auxiliary parts, as can be seen here. So which is including only breaker circuits and also some rectifiers units. So FPGA 1 and FPGA 2 are running the body of the power system, including slow switching frequency converters, the generation and breaker circuits, while the third FPGA in blue here is reserved to simulate fast switching frequency inverters and the machines. So here in this table, we are summarizing the power decoupling element type and also the decoupled node. We use two type of decoupling elements. The first, at the AC side, we were using the stub line method, and we have 6 power decoupling locations. And the ideal transformer method to benefiting from the DC bus at the output of the rectifier to perform the decoupling between FPGA1 and FPGA3. This method is simple and consistent of measuring the DC voltage, sending it to feed the inverter, and then measuring the inverter current to re-inject it in the DC bus. So from the FPGA programming firmware side, we developed or we designed two firmware. The first firmware is used to flash or to program the first and the second FPGA. So this firmware includes two EHS or two FPGA electrical solvers, as can be seen here, and some SFP modules to ensure the communication between FPGA to send the stub line and the ideal transformer decoupling methods signals to the other FPGA and vice versa. The second firmware is used to simulate the machines and the fast switching frequency converters. So the firmware includes one solver, one EHS solver, and 8 PMSM motors. It integrates also a PWM generator inside the FPGA to generate accurate PWM signals. So we performed also several tests to validate the platform with 3 FPGA boards interconnected together, running the complete B787 power system. So we started by steady state and pulse enable disable tests, always compared to SPS offline, and we were getting really impressive results, less than 1% of error everywhere during the dynamic tests. Also, here we show a step on the torque, on the low torque. And also during the fault series of tests, here we show one of the most complicated tests, single phase fault, really closer to one of the decoupling elements. And we can see compared to SPS offline, we have always a very good resolution. So by this series of simulation using only the simulator standalone, we could validate the accuracy of our solver and also the robustness of the platform in terms of numerical instability. So now what we are doing is we started to integrate our platform in real HIL applications, real control testing. So the first application we worked on, or we are still working on, consists of DSP-based control testing that will integrate a field-oriented control in order to regulate the speed of the machine here. So we have the OPAL-RT simulator shown here, including the FPGA parts. This FPGA parts will run one principal feeder of the Boeing power system, consisting of a a voltage source connected to an AC DC AC converter driving the PMSM. And we have also this, to do this integration, we follow the real-time simulation integration process, which consists first of a software in the loop simulation to validate the control algorithm. So first, before integrating the algorithm of control in the real device, we simulated this algorithm in real time using the available cores that comes with the platform. So we simulated this algorithm, and we sent the duty cycle, the generated duty cycle, to the FPGA PWM generator here to control the circuits. So once it's validated, we send it to the DSP, and we connect it to the DSP to read the analog signals that are needed to perform the control. At this step, what we can do is we can scale well the signals and make sure that the signals are arrived to the right destination. Then what we perform is a loop back test. So what we did is to validate the assignation of the digital input of the simulator. So using the digital output module integrated in the simulator, we output the signals, the PWM signals, and then we inject them back using the digital input module. So this will validate first the assignation, and from the analog side, we are still reading the analog out at the controller side and showing them, make sure that they are well received and accurately with the right gains and offsets. So we have actually some preliminary results compared also always with SPS offline, and we are still closing the loop. We are in this step, the third step, which is the closing the loop with the controller. So also, I need to mention here that the user interaction is done easily using our host computer, any laptop that can be connected with Ethernet to the simulator or wireless. So we can send the manual control to vary, for example, enable the pulses, vary the speed reference, control any breaker specifically. Everything can be done from the computer host of the user. So this is one application, one real application to test the platform, and we started also another real application, another PHIL application this time, which consists of a motor drive emulation. As can be seen here, we have the drive, the feeder of the Boeing here that is simulated under the FPGA. And here, just at the output of the rectifier, we are applying an ideal transformer decoupling method. So the measured voltage is sent to a real power amplifier that will generate the real voltage. And then we have the emulated part, which consists of a 12 IGBT inverter with the PMSM, the 6-phase PMSM motor. So to emulate this drive, we used another power amplifier available here in our laboratory. So this amplifier normally is used or controlled in control mode in order to generate the real current, the real power. So we have we'll have two amplifiers that are forming a back-to-back configuration together. So the latency, or the total latency that we measured, is between 3 to 5 microseconds, which is very good, very low. The amplifier one, the first amplifier here, is controlled in in voltage mode with a bandwidth of 3 kilohertz, while the second one is controlled in current mode to ensure the real current, and the bandwidth is 10 kilohertz. So yeah. So to recapitulate, we have developed a more electric aircraft multi-FPGA power system simulation test bed, which is scalable, means that we can vary the number of computation units as we need. In terms or in a software point of view, we have demonstrated an accurate electric FPGA solver called EHS. We showed a robustness solution toward numerical instability while decoupling the power system to assign the multiple subcircuit to different computation units. Using the analog and digital input outputs, the platform can be easily connected to a real device under test, can be controller, can be a protection relay. Also, we can test real components such as battery with the converter by connecting it to the simulator through a real power amplifier. The solution also integrates many communication protocols that, as can be seen here, that leads to connect different components while offering the same standards. So this table here summarize the performance and the technical details of the basic solution. The basic solution can come with up to 3 Intel processors that can be used, as we said, to simulate slow switching frequency phenomena and the mechanical parts, controllers in software in the loop simulation. We have one FPGA board that can integrate 2 EHS solvers. And we have 4 analog digital models that are flexible for the basic solution. And also we have for each solution we have 16 high-speed communication ports to communicate with other FPGAs. So before going to the question, I want to show you an example of how we can do the testing or the testing in real time. We have recorded this video that is simulating one principal feeder of the aircraft. So here is an interface that show how we can apply manual faults. We can test the system in real time while the circuit is real time running on the FPGA. So we can start the question session.
Thank you, Amit. Thank you, Amin. Like it was really interesting to see like where we are now with all the FPGA solver and the MEA topics. So now it's the period of question, and actually, like as Amin said, like we'll run like the small demo in the background. So just to give you a grasp of like what we can do, like actually this is like all the concept that Amin tell you today, running in our demo. So like you can go to the question feed and actually ask your questions directly in the chat. Actually, we have one here for